Okay, so I have started the recording.
Okay.
Okay, so are you able to see my screen, both of you?
Yes, it's clear.
Okay, so this is the chapter number 8 of the Killister book, right? And it is about the mechanical failure.
Okay.
Okay, so when you see this word mechanical failure, so what comes to your mind?
I don't have an idea for real.
Okay, so what do you think about this word failure? Am I audible to you?
Yes, but I think we don't have an idea.
Okay, okay. So in general, failure is anything which breaks up, right? So, for example, if I have this material and I weld it some over here, right? So if I apply a force or a bending moment to this body, then it will break
It
off.
will break.
Yeah, it will break up at the point of welding.
Yeah, yeah.
So this is what we call mechanical failure, right? So in this chapter, we have to analyze these failures, so how they can lead from cracks to failure, and okay, so how this fracture is quantified. So how can we quantify this fracture in terms of mathematics? For example, have you heard about the famous movie in which the ship is destroyed?
No, I don't think that I heard it before.
Titanic. Have you watched this movie?
Titanic. Yeah. Of course.
Okay. Okay. So in the Titanic, right? In the previous era, there was no knowledge about the mechanical failure, right? So when they were designing the ships, so these were some mechanical engineers who were designing this specific ship.
Yeah.
So they have no idea that when the ship will go to the seawater, so the seawater temperature will be lower than the laboratory temperature on which they perform the design calculation of this ship. So it lead to a major catastrophic and loss to millions of people lives, right?
Yes.
So as an engineer, as a mechanical engineer especially, you have to analyze, you have to design these kind of things so the public and the economic losses are minimized, right? Similarly, if you look at this computer chip, so this computer chip is loaded by a thermal loading. So you have to design, you have to select a suitable material for this chip so that it doesn't melt, right? Also, if you look to our legs, right? So to our legs, so when we grow up from child to adult, so our bones become strong. So they become strong because our body mass is increasing. So in order to resist this load, or in order to point this load, we need stronger bones, right? So that's why our body have stronger bones when we become adult. Okay, so basically we have two types of failures, two types of fractures basically. The one is we call the ductile fracture, and one we call the brittle fracture. So do you know about the ductile materials and brittle materials?
I think that ductile comes maybe
Okay. So ductile materials, when you think about it, like, okay, so this is an electrical wire, right?
Yeah.
So inside it, you have seen the copper wires, right? Similarly,
Okay.
you have seen this disk, like currency, right?
Mm-hmm.
So, and similarly, you have seen the plates which are formed from copper, right? So all those
Okay.
materials, from which the wires, the disc, and these plates are made, so they can be classified as ductile material, right?
Mm-hmm.
And the brittle material, like glass, right? Glass, ceramics, and etc. Right? So the brittle materials, when we apply some load, so they break off like glass, right?
Mm-hmm.
Okay. So when you try to stretch, okay, so this is let's say this is a ductile material, and you apply some force F, tensile force, right?
Okay.
Okay. So when I applied some tensile force to this object, right? So after some time, it will elongate, right? It will elongate, right? And this area will be decreased. So after
Right.
some time, this material will break off, right?
Mm-hmm.
So
Yes.
this elongation is what we call the plastic deformation.
The plastic.
Yeah, the plastic deformation, right? Okay. And let's say if this was a brittle material, right?
Mm-hmm.
Okay, so if this was a brittle material, then initially, okay, so this was for ductile, and for brittle material, okay, so let's say I have this specimen, right? And I apply some tensile force from both sides, right? And after some time, you will see that it will not elongate, no elongation. So when we see this type of material that in which no elongation occurs, then it is called the brittle material, and the fracture associated with this material is called what we call the brittle fracture, right?
The brittle fracture. Yes.
Yeah. Any question in these two topics? Do you understand it fully
It's
now?
clear.
Okay.
Yes.
And what
I
about
understood.
Hamza? Hamza,
Yes, yes,
it is clear to you?
clear. Yeah.
Okay. So catastrophic means that it will not. For example, we will not see that this material is leading to fracture, right? So we will see that there is no fracture associated with this, but automatically, suddenly, it will break off, right? So when this automatically breaking off occur, we call it the catastrophic failure, right? Okay,
Yes.
so in this slide we have basically the classification. We will basically analyze the ductile and brittle fracture. Okay, so when you, let's say this is my specimen, right? This is my specimen, and I applied some tensile force on it, right? So this is my specimen. So have you studied the chapter number 7 carefully? Chapter number
No, the chapter number 7 is not included with us.
chapter 6.
Chapter 6, yes.
Okay. So do you know about this diagram? This something like this.
No, I didn't cover this one.
The stress strain diagram.
Yeah, you can teach us this one.
Have you not studied the stress strain diagram?
We studied it, but I didn't cover it.
Okay, so I suggest you that please go through these materials. So if you go through these materials, then it will be very easy for you to understand these fractures, right?
Yeah. Okay.
Okay. So on this slide, we are basically analyzing the ductile and brittle fracture. So I told you that I load the specimen, right, with a force F. Okay.
Okay.
So when I load this specimen with a force F, so after some time, this is my specimen, right? So you can assume that it is a uniform block, right? So when I apply some force F, right? So after some time, we see these sharp edges, right?
Mm-hmm.
So when they are deformed in such a way, then we said that it is a very ductile material, right?
Yes.
And when this kind of teeth-like structure occurs, then we say that it is less ductile. And when there is no sharp edges, there are no sharp edges, right?
Right.
So this is what we call the brittle material, right?
Mm-hmm.
Okay.
Yeah, I got it.
And it is written here that brittle material gave us no warning, right?
Yes.
Do you understand this sentence, no warning?
Yeah, I understood.
Okay, so it means that when we are applying this force F on the specimen, right? So if you look at it just before the fracture, then you will not notice any symptoms of the fracture. But if you look to the ductile material, then it is elongating. It is elongating after some time, right? So from this, you get the idea that the fracture is happening here, but you will not get any idea that the brittle fracture is happening. So it is very convenient. It is very necessary for any engineer, especially a design engineer, to know about the brittle fractures. And it is sometime analyzed the brittle fracture or we call the ductile fracture. It is the reduction area or the elongation in length, right? So we sometimes analyze this fracture as a reduction of area, this cross-sectional area, right? Or the elongation in the length. Okay. So this ductile material, right? So if you see, as I told you already, let's say this is my 5. And I apply some force, tensile forces on it. Okay, so when this ductile fracture occurs, so this pipe, it will elongate, right?
Yes.
And what we call this reduction area, this is the area cross section. If you zoom it and the cross section will look like this, right? But after fracture, the cross section will become reduced. So from this reduction, we can see that it breaks into 2 pieces, right?
Yeah.
So when this specimen breaks into 2 pieces, this is what we call the ductile failure. And let's say you have a glass, right? Okay,
Glass, okay.
so this is a glass, and you throw a stone to the glass window.
It will break.
Yeah, it will break, but it will break into pieces, many pieces, right?
Two pieces, yes, many pieces.
Yeah.
If it's many pieces, it will be a brittle flavor.
Yeah, you are very right. It is. It is.
Okay, I get it. Yeah.
Okay. And Hamza, are you understanding?
Yeah, it's clear.
Okay. Okay. Now we come to this moderately ductile pressure. As I told you on this slide, that when there are the sharp edge, when the sharp edge is one, right? So it will be very ductile, and when the sharp edges are many, like teeth, so this is what we call the moderately or the less ductile, right?
Yeah.
So let's say this is a stress, right? Do you know about the stress definition? What is the definition of stress? Stress is basically force per unit area, right?
Yeah. F of A.
Yeah, and it has a unit of Newton meter per square or Pascal,
Yeah.
right? Okay, so my question from both of you,
Yeah.
my question from both of you, what is the difference between the pressure and the stress? They both have the same units. What's the difference? Can you tell me, Omar?
I'm not sure.
And Hamza, what about you?
No idea.
Okay. So let me clear your concept that what is a stress and what is a pressure, right? Okay, so this is the body, right? This is a spherical body.
Yes.
Okay, so this is a spherical body, and it is dipped in a container, right? This container is full of water, right? So the forces that act on its surface, right? So the forces that act on its surface, we can call it F divided by the surface area of this sphere. So this is pressure, right? But when I break this sphere into two pieces, right? Like this, then this pressure on this internal areas, I repeat, internal areas. So internal area, force per unit internal area, it is what we call the stress, right?
Yes.
So the internal pressure or in the internal intensity of the force is what we call the stress. Do you understand?
Yeah, I get it.
Okay, so can you repeat it?
Yeah, you said that for the pressure,
Okay.
it's like it's one. It's not like the stress.
Yes.
It has two. Yeah. Yeah, I mean, it's like this.
Okay, so the external forces, they are causing the pressure on the body, but the internal forces, internal, right? Internal forces, they are causing the stress,
Internal force.
right?
Yes.
So the internal forces, they are causing the stress,
The stress. Yes.
right?
Yeah.
Okay, this is a very good concept for you, because in the future, in the next semester, you will study the material, the mechanics of materials.
Yeah. Yeah.
So this this is the foundation. This fracture and this failure are the foundation for these courses, right?
Is the pressure and the stress has the same definition?
No. I told you it has the same unit, right? It has the same unit.
But not the same definition?
But the stress is internal and the pressure is external, right?
Yeah.
So now you understand fully.
Yeah, I got it.
Okay, so let me clear my screen, and then I will tell you what these two pictures are showing us. So I hope you have now fully understand the concept of stress and pressure.
Yes, I got it. I understood.
Okay. And okay, so this is basically this is showing us the this is the stage number 1, right? This is the stage number 2, this is 3, this is 4,
Yes.
and this is the 5th stage, right? So in the first stage we apply some stress on this body, right?
Mm-hmm.
Right, so when we apply some stress on this body,
what is called this unit? This unit that you write?
This is called Pascal.
No, I mean I will write this one. What is called?
This?
Yes.
This is called sigma.
Sigma. Yeah, okay.
Sigma. This is called sigma, right?
Okay, sigma.
Okay. So this sigma, right? This is representing the stress, and we are representing the pressure by P, right?
Yeah.
But this pressure is what we deal in the fluid mechanics, right? Fluid mechanics.
Fluid mechanics.
Yeah. So you will also study this fluid mechanics course in the later semesters, right?
Yeah, next semester we will study this.
Yeah. Okay. So when I applied this sigma stress on the body, then after some time you will see that these micro cracks, right? If you analyze it with the help of a microscope, right? So you will see that after some time these crack occurs, right?
Mm-hmm.
And this crack, they will try to elongate, right? So for example, if this one crack is like this, then after some time it will become bigger, right?
Right.
So when they become bigger, they will combine with each other, and they will result into a big crack. Okay, so when this big crack is formed, then this big crack, it will try to at the edges, right? It will try to elongate at the edges. And when this crack reached this outer surface, then it what we call the fracture.
Mm-hmm.
Okay, so you 1, 2, 3, 4, 5. So you understand these 5 stages of the ductile fracture?
Yeah, clear.
Okay, Hamza, can you explain the stage number 2?
Yes, it has many
Number
stages.
2.
Yes.
It's the first breaking. It will be in the middle. Small breaks.
Yes.
And then they will combine together and be big.
Yes, big. And Umar, what is happening in the
will be breaking the
edges, right?
And stage number 4.
Yes.
It has the break. It has bigger.
Yes.
Okay.
Yes.
And it will in the last stage it will break it totally.
Yes. So in the fourth stage, this bigger crack, this will propagate, or we can say that this will try to expand to the edges, right?
Yes.
Okay. So this is the moderately ductile fracture. Okay, so when we microscopically analyze these surface, right? This is the zoom image of this, right? So when I zoom it up to 1,000 times, then this becomes this, right?
Yes.
So we will see that there are some particles that are leading to this fracture, right?
Yeah.
And this is what we call the nucleation sites. So in the next chapter, the phase diagrams, you will see that what is meant by this nucleation sites, right? Okay, so this
You
is
mean I mean after breaking and the
yes,
small things it's called nucleation.
yes, yes. So these are
Yeah, I'm just asking.
okay. So these are basically the particles that are responsible for the failure, right?
Yeah.
Okay. The fracture surface of the tied cord wire intention. So this is the fracture surface. So this is the wire, right? Tied cord. So this is a cord, right? I apply a tensile force, or you can call this a tensile stress. So when they are loaded in tension, then they break at this edges, let's say, and this edge is zoomed here, right? So when we see that, it is like a cup and cone shape, right? Do you see that? Okay, so what is the difference between this and this?
The second are brittle.
Yes. Okay, okay. So this is the ice cream cone, right? Right?
Yeah.
This is the ice cream cone,
Yes.
and you put some ice cream in it, right? So it will become like this. Right? So
Yeah.
this is what we call the cup, and this is the cone, right? So this is the cone, and this is the cup, right? So when this cup and cone structure forms like this, so this is what we call the ductile fracture. And the brittle fracture, there will be no cup and cone shape, right? It will be a straight edge, right? Like this.
Yeah.
Okay. So now you understand this slide.
Yes.
Okay.
Yeah, straight. Yeah.
And the brittle fracture, right? Okay. So the brittle fracture, basically, this is, if I zoom in, then it is what we call the micro crack. So in every material, you have to understand this point. In every material, there are micro cracks, right? Every material in the world,
Okay.
right? So they have some imperfections. You may have studied the chapter number 2 very.
Yes, yes, of course.
Okay. Chapter number 2. So you have studied the imperfections. I assume that you have studied it, right?
Yeah, yeah.
Okay. So, okay, give me some answers, right? So this is, are you able to see it?
Yeah, the cube.
Okay. So what kind of structure is it? What kind of cube is it called? And this particle is in the middle. Can you name this cube?
Oh, I forget.
Okay, so this is the body-centered cube, right? BCC.
The body centered BCC. Yeah.
CC.
Because the one particle is in the middle, right?
Yeah.
And this is the
Yeah,
sample,
yeah.
and this is the sample cubic, and one is the face-centered cube, right? So on the face, if I draw the face of the face-centered cube, then there will be a centered particle, right? Okay, so this was the knowledge from. So I'm telling you that the brittle material, what we call, every material has the micro cracks, and these cracks lead to the failure, right? So from these cracks, the failure originated. Okay, so you also have studied, you also have an idea about the grains and the grain boundaries. Right? So this is basically the diagram for the brittle fracture, for the steel, for this steel, for the propylene, which is a polymer, and aluminum oxide, which is basically ceramic, right?
Ceramic.
So when you see that the 304S steel on the microscope, you will notice that the grain boundaries are not regulars, right? So they are not regular. And also, if you see that, then there are some cracks. This is basically showing you these dotted lines. These are the cracks, right? So it is basically showing you that these cracks are responsible for the brittle fracture, right? Also, in the polymers, if you look, then there are failures, right? And if you see this aluminum oxide, then these irregularities. So these irregularities are causing the brittle fracture. Okay, so ideal and real materials. Ideal versus real. Okay, so what's the difference between ideal and real? Am I audible to you? Hello?
Yeah, but not sure.
What? Umar?
Yes, I'm with you.
Okay, so are you here?
Hello?
Yes.
Yes. Yeah, I'm with you.
Are you listening? Are you listening? Hamza, are you listening?
Yeah, here.
Okay.
Can you?
Okay, so
Can you hear me, Doctor?
Yes. Yes, I can hear you.
Okay.
So the stress strain behavior at the room temperature, right? So this you have to remember, this is at the room temperature. Room temperature we assume to be 25 degrees centigrade or 298 Kelvin, right?
Yeah.
Okay. So when we perform the stress strain test, the tensile stress, right, on this specimen, then we obtain this diagram, the stress strain diagram, right?
Yeah.
Okay, so you know the definition of the stress, right? So stress is the internal force per unit the internal area, right?
Area, yes.
Yes, and what about this strain? What is the definition of the strain? Hamza, do you have any idea about this? What is the definition of the strain?
No, no idea for that.
And Umar, do you have an idea?
No, I'm not sure, but maybe there is a force. Maybe I don't know.
Okay, so the strain is what we call the change in the length divided by this original length. Okay, so let me explain this term to you, right? So this specimen, this has a length L, right? And after some time when I apply the force, after some time I notice that this specimen, if I draw it horizontally, the change in the length delta L occurs, right? So this change in the length delta L divided by this original length, it is what we call the strain, right?
Yes.
Okay.
So how will you define the strain? The change in the length divided by this original length, right? And it has no units, right? You
Change in
don't
the length over length.
what?
Change of the length over length.
Yes,
Delta L.
over the original length. It is delta L, right? Delta L. Let me make
Delta
clear.
L over L. Okay.
So this is delta L. Okay. Okay, so we are analyzing the stress strain behavior at the room temperature, right? So
yeah,
are you able to see this black line? This black line?
Yes.
Okay, so this is the perfect material which has no cracks, right? So the ideal material we call which has no cracks. Is this possible that a material has no cracks? Hamza? Hamza?
No, I don't think so.
Yes. Okay. So this material has no cracks, and this real material, it will always have cracks, right? So we assume for the ideal
always
material.
has cracks.
What?
Always has cracks, the real materials.
Yes. And for the ideal material, we assume that there are no cracks, right?
Yes.
Okay, so this is basically the stress strain behavior for this E by 100 and E by 10. We call it as the brittle fracture, right?
Yeah.
So we notice that the tensile strength of this material is very, very much less than the perfect materials, right?
Tensile engineering, it's less than perfect materials.
Yes. Why it will be less? Why it is less? Okay, so in exam, if you are asked this question that why the tensile strength of the engineering material is much less than the perfect materials, so how will you answer this? I told you a few minutes ago.
Because ideal has no cracks. And
yes, you are right. Yes, right.
And real materials has always cracks.
Always cracks. So real materials, it we call the engineering materials, right? And the ideal material we call the perfect materials, right?
Yeah.
Okay. So do you hear about the DaVinci?
No, I didn't hear before.
The Mona Lisa paint, you heard about it? The Mona Lisa.
Yeah.
So the
DaVinci.
Yeah.
The painting.
Yes.
Yeah.
Yes, the painting was made. The Mona Lisa painting was made by Da Vinci. The Da Vinci was an engineer. He was an artist. He was like everything, right?
Yeah.
Okay. So he noticed that the longer the length of the wire, the smaller the load for the failure, right? So if you increase the length of the wire, right? So this is the length L, and this is for the second wire, right? This is the length L dash, right? So DaVinci, about 500 years ago, he noticed that as you increase the length of the wire, then the load for the failure becomes smaller and smaller, right?
Yeah.
So how was he right or wrong?
Again, doctor.
Yes. Was he right or wrong?
Can you repeat it again, please?
Okay. So the DaVinci, the famous DaVinci, he observed that when you increase the length of the specimen, right? So okay, so on this slide, if I will draw, okay. So this is my specimen, right? This is a force, and this is another specimen, right? And it has a larger length, right? The larger length of L dash, and it has a smaller length of L. So DaVinci observed that the longer you make the length, then this less load, less force, less this force will be required for the failure. So was he right or wrong?
Yes, he's right.
Why he's right?
I think wrong.
Yeah, so you have to notice this definition,
Yeah,
right? And the reason are the
because
Yes.
more length equal more force, not longer.
yes. So there are
Will be more.
yes, there are two reasons for this. The flaws or the cracks, they cause the premature failure, right? So the premature means that we are not go to the limit which are for the perfect material, but they fail before the perfect material, right? So the reason for this is the flaws, and when we elongate the length, it means that there are more flaws, right? So on this slide, if you notice that this length is increased, right? So it will have more flaws, it will have more cracks than this material, less cracks, right? So that so DaVinci basically observed this, that the more cracks in the longer length, so that's why it will require a small load for the failure.
Yeah.
So now you understand the DaVinci.
Yes, I understood.
Okay, so can you repeat?
Yeah, okay. The DaVinci, he said that if there
Yes.
is a long,
Yes, a long material.
a long material, yes.
Yes.
Okay. Less force that
Yes.
will make
The material break.
cracks, you know, the break.
And
break, yeah.
And what were the reason for this?
Because it's too long. I mean, if it's too long, the less force will break it.
And why the less force will be required? Because there are more cracks, right?
More cracks, yes.
Okay. So now you understand the DaVinci idea.
Yeah.
So I advise you to please note down these important points with you, right?
Yeah, of course.
Okay. So are you writing? Are you writing on the? Do you have pen and paper or tablet, etc.?
Yeah, I wrote it in the paper.
Okay. Okay. So now this sigma m and this sigma naught, right? Okay. So this is a crack, right? This is a crack.
And also we can come back to this recording and see it again.
Yes. And one thing more.
By the flow.
Okay, so
Question.
if you are studying this lecture, right? If you are studying this lecture, and if you face some problem, right?
Yeah.
You can ask me anytime, right? Anytime on the WhatsApp, right? So you both. So if you have any problem, then I will discuss it in the on the WhatsApp. But if it is not possible on the WhatsApp, then we will have a meeting anytime, right?
Okay.
Okay. So I gave this opportunity to all my students, right? Okay.
Okay, thank you.
Okay. So this is the stress. This is the stress I applied initially, right? So I will represent it with sigma naught,
Yeah.
right? Okay. So during at this point, if you observe this, then this stress is concentrated, right? Concentrated. And it will become sigma m, right? This stress sigma naught will become larger at the edge of this crack, which we call sigma m, right? So do you understand the difference between sigma m and sigma naught?
Can you repeat again?
Okay. So sigma naught is the initial stress.
The initial. Yeah, I got it now.
And sigma m, it is the concentrated stress at right.
Yeah.
So this is the concentrated. So now we have to relate this sigma naught and sigma m to each other, right? By the help of this crack.
Yeah.
Okay. So have you studied the calculus? So what kind of shape is this? Can you answer me? Do you know about this shape ellipse?
Ellipse.
Ellipse? Do you know about this?
Yeah.
Okay. So this ellipse, this has a radius of curvature PT, right? PT.
Yes.
So this is the radius of curvature PT, and it has the longer side of plane 2A, right? And this from this up to this is the radius of curvature PT, right? So we can write this sigma m equal 2 times sigma naught A divided by PT power 1 by 2, right?
Yeah.
And we see that PT is the radius of the curvature, A is the length of the crack, right? A is the
It's the Oh, oh, okay.
A is the half length of the crack, right? A is the half length of the crack. PT is the radius of curvature. Sigma naught is the applied stress, and sigma m is the stress at the crack tip, right? So I tell you that this is the concentrated stress. So we can relate by this mathematical equation, right?
Yes.
So now you understand it fully? Do you understand this concept of sigma m and sigma naught and how they are both related with the help of this crack length and the radius of curvature power 1/2? And this 2 times square root of a divided by
Yeah,
rho
yeah, I
rho
understood.
of t.
Yes.
This is a constant. This is a constant. So I can write it with the kt, and we can write it's kt sigma naught, right? So that's how we can relate the sigma m with the sigma naught. And okay, so on this figure, which we derive this equation at sigma m equals sigma naught square root a divided by rho t, right? And we can write 2 times. So we can write this term as kt, right? So it is kt sigma naught. So if I plot this stress, right, near this tip edge.
Mhm. Yeah.
So this stress, when this force reaches to this, when it is reaching, so it will grow up like a parabola, right? And at this tip, it will become longer and longer, and it will go to sigma m. So remember this sigma m, it is always greater than sigma naught, right?
Yes.
So
Yeah.
that is what we call the
Because
constant.
sigma naught is the initial.
Yeah, initial. You can assume that at this point it is sigma naught, and at this point it is sigma m, and they both have a parabolic relationship or exponential. They are exponentially increasing, right? So this is sigma naught, and this is when I reach this crack point, so this is sigma m, right? On the both sides. So this is basically plotted here. And this kt, we derived this equation, right? Sigma m equal kt sigma naught. Sigma m is equal to kt sigma naught. So this kt, if I solve for kt, then sigma m divided by sigma naught equal to this. And this kt, it is written here that it is what we call the stress concentration factor, right? So kt is stress concentration factor, right?
Yeah.
Okay, so this r by h ratio and the stress concentration factor, they are plotted here. So if we increase the r by h ratio, right? So what is r? R is basically the radius of the curvature, right? And h is this length, right? So if we are increasing this ratio, right? So this radius or this stress concentration factor becomes 0, right? So it is going to 0 when we are decreasing this. Sorry, it goes to 1 because it has a value of 1. So it goes to 1 as we are increasing the r by h ratio. And as we are decreasing the r by h ratio, so this stress concentration factor become increasing, right?
Yeah.
So do you understand what I'm saying?
Yes, yes.
Yeah.
Clear.
Okay, so in the tomorrow lecture, inshallah, we will study this crack propagation, right?
Is there a question we can solve by equation?
Yes. Yes. Let me try to give you some
By
problem
these
from
equations, is there questions?
what?
Yes, please. To be
Okay.
clear.
Okay.
Yeah, just to be clear.
One time, I have to plug in my battery charger, right? 1 minute.
Okay.
One minute. Okay, so are you here?
Yep.
Yes.